So today we are going to go over introduction to large language models. So that have become very popular in recent years. We touch upon the basics. We don't go into too much of details. We'll cover introduction. I'll also go through one example of a neural network in R, since these models make use of neural networks in a big way. And also we have been using R that will help us to have a basic understanding of like how neural networks work. And then one of the large language models by OpenAI, like most recent one is GPT-4. So we will look at one simple example and some interfaces that are available like Olama, Hugging Face. So I pulled some data from Google Trends. So if you type LLM and compare the search term LLM with a related term called deep learning, because LLM is part of deep learning. So you'll notice that at some point, somewhere here, interest in LLMs started to increase significantly. And especially since ChatGPT was released by OpenAI. If you look worldwide, like where people are searching for these terms related to LLM, the top term is ChatGPT LLM, and then you have GPT, LangChain LLM, OpenAI, Hugging Face. Now, to give a big picture overview of where LLM fits in, so you must have seen this diagram where AI is like the overall thing, and there are so many different kinds of applications of AI. Now, some of those applications make use of machine learning methods, and a subset of these machine learning methods are deep learning, where basically we are using very deep neural networks. So by deep, we mean multiple layers of neural networks. And within that, you have a subset which represents LLM, large language models. So here we are talking about text data mainly. It could be in any language. It could be English, it could be Spanish, or any other language. And these models are typically nowadays, you may come across, they are not just working with the text, but they're also good at working with the other unstructured data like video, audio, images, and so on. But LLM is a subset of deep learning where we are more focused on creating models that focus on languages. So these are some examples. Text summarization, especially like if there's a voluminous text, it can be summarized very easily by these models. And it comes very handy if a company, let's say Amazon, they have so many customer comments and they want a quick summary in certain way, like it could be sentiment analysis, like whether the comments are positive or negative. So those kind of summarizations can be done very easily by using these models. They also help with the code generation and auto completion. It doesn't matter like which language you prefer, whether it is R, Python, or C. So these models have basically, they can help with code generation and auto completion. And many of the big tech companies, they also talk about it, like how much of their code is being created by AI. Another application could be chatbots or virtual assistants, language translation, almost real-time language translation. You can very easily convert from one language to other language. Sentiment analysis is very common. This is a repeat, actually, code generation and auto completion. Sentiment analysis is again a big topic, especially when you are working with text data and social media data, for example. So it's so much of information. So people want to use sentiment analysis to be done to get a quick idea. One example is, let's say during presidential debates, before and after, what people are talking about on social media can be analyzed, and then those political parties can see whether their strategies they adopted is working or not. Are the sentiment converting to positive, or they are still negative, and so on. Or new product releases. So before and after, what people are talking about on social media can be used for data cleaning and transformation, and automated documentation is another application. Tutoring and learning support. One of the large language models actually by Google, you can go in and share your screen, whatever you are working on. It could be Excel file, and it will understand that you're working on an Excel file, and let's say you have lots of data in that, and you can talk to that assistant. Let's say you want to do some kind of pivot analysis, pivot table from some of those columns, and you ask, and it will guide you actually by talking to you, like how you can do the pivot table very easily. So those kind of tutoring services are also available now. Sometimes it may make error, but I think it is improving almost every day. And then you have like creative content generation. That's a big application. This chart, I got it from market.us. They have some data and they are projecting how big this market of just one part content creation will be by 2034. So if in 2024 we were talking in terms of $2.4 billion, it is expected to grow to almost $75.5 billion in just 10 years or 9 years from now. So that's like exponential growth in just one type of application. And there are many companies that are using large language models for so many different kinds of activities. So JP Morgan Chase, for example, they have been known for using it for categorizing documents into different categories. That's a big challenge. Airbnb, they use it for generating platform content. Delta Airlines, they have Ask Delta chatbot that uses LLMs. Washington Post has something called Heliograph, and they use it for content creation. Amazon uses LLMs for analyzing product reviews. Their websites, they get like a lot of information, and it is almost impossible for a human being to analyze all the product reviews, like do a sentiment analysis and see whether customers are positive, negative. So these are just sample, but there are many other companies that are using it in a big way. So what is a large language model? So if you simply focus on the word large, so here it basically means, so these models are trained on enormous data, huge amount of data, and these data have billions and trillions of words. So that is large. Also, they have vast number of parameters. So earlier I talked about they use some kind of neural networks, and these neural networks basically have a lot of neurons, and parameters are related to them. So vast number of parameters, and they also require significant computing resources. When you have so much of data, it is not possible to run these models on a simple, like any laptop. You really need a very powerful computing resources. So this is an example of GPUs used by top LLMs. So you have something called GPT-3 by OpenAI, and the model size is 175 billion parameters. And estimated GPU usage, 10,000 GPUs, NVIDIA V100, and to train these models, it takes several weeks. Latest one, GPT-4 that came last year by OpenAI has about 1.76 trillion. So this is the estimate parameters, and they use about 25,000 to 30,000 NVIDIA A100. And to train this model, it took multiple months and obviously different phases. One by Meta Llama, which has 70 billion parameters and about 2,000 GPUs, approximately 21 days. Google has the Gemini. They require about 30,000 GPUs. Grok by Elon Musk uses about 16,000 GPUs. So you can see like how much NVIDIA GPUs are being used, and no wonder NVIDIA has been doing very well for last few years. If you look at its stock price, it has been going up and up. Although like recently it has come down a bit, but it has been going up and up. Now, when you look at language, so it is talking about a human or programming language that the LLMs process and also they can generate. And models So sophisticated machine learning algorithm. So in this case, it is neural networks, and it is designed to understand and generate human-like text, because it is trained on huge amount of data. Obviously, it makes some mistakes sometimes, but anytime you get output, you will see that grammatically it doesn't make much error. It can make some errors like about the facts, but grammar and other things, it is almost like perfect. So this is a picture of a neural network. So it has basically three different parts. These are actually three different layers. First one is the input layer, and the last one is called output layer. And in between, which is like hidden, is called hidden layer. I'm only showing you like a very small one, just two hidden layers here, but it can be in hundreds if you're talking about like large language models. So it can have much more than what we see here. So this is a small example using the data that we have already used. Applicants who are applying to a graduate program, those applicants have provided data on GRE, GPA during undergrad, and rank of the college or university from where they are applying. So using these three, we are trying to figure out whether the applicant should be admitted or not. I ran this through a very simple neural network. It has just one hidden layer, this one, and only one neuron, like very, very simple, so that I can show you like how we get what we get here. So let's go to that and then we'll come back. I'll get this R code, copy and paste it here. And then this pops up, says package neural net. So that's the package we need for running the neural networks is not installed. So I'll click on install. So I'm reading this CSV file, binary.csv, directly from GitHub. If you look at the structure of the data, you can see that this is a familiar data set we have. 400 applicants, 4 variables, and admit is integer. Now, one thing about the neural network is it needs numbers. So even when we have unstructured data like a text, so that has to be converted into numbers. Or if we have image data like pictures, so even that needs to be converted into numbers. So pre-processing of unstructured data is like an important step before you can run any neural network model. So although like all these are already numbers, one more thing that we do for the neural network is we do some kind of normalization. And one of the popular ways of normalizing data is min-max normalization. So if you look at GRE, for example, and let me type in console hist data dollar GRE and run. So these GRE values are from 200 to 800. So what min-max will do is you take each data point and subtract minimum of the data point. In this case, it is going to be about 200, and divide by maximum, which is about 800, minus minimum, which is about 200. So if you run this and come back and check histogram again, you will notice that now the values are between 0 and 1. So that will happen for each and every variable. Admit, we don't have to do anything because already it is 0 and 1. So now I'm splitting the data into 70-30. So training 281 applicants, testing data has 119 applicants. I see a hand raised, Jeremy.
I just wanted to ask about 70-30. Is that arbitrary or is that an optimal split?
There's no specific reason for that.
Okay.
Usually we want to the idea is to reserve something for the testing. You don't want to give everything for training.
Thank you.
But it also depends on the data. If you have millions and millions of rows, and if computing becomes too slow, depending on what machine you have, then for training, you may have to go for a much smaller number, like even sometimes less than 1%. But here, running 70% of the data in training, we have no issue because it is only 400 rows of data. So it's not really huge data set. Once we have this split, I'm going to use this neural net library. If you don't use any set.seed, every time you run a neural network model, you are likely to get maybe a different outcome. It's not like linear regression where B0, B1, B2 will have exactly same number. But with neural networks, so there's no guarantee, like things change randomly. So we have to set a seed, and using the function admit versus all three remaining variables, and the data is training. For hidden, I'm going to change this to 1 first to be consistent with the PowerPoint where we had just one hidden layer. For error, maybe I can type it here, neural net. So that function, you can see there are many things that we can do here. Error.fct. So this is used for calculating the error, and there are two types actually. SSE, sum of squares due to error, and CE is cross entropy. But let me run this, and the model is stored in N, and then if we run plot N, it will plot that neural network. Since I'm using exactly same settings, you'll see the numbers are same. So for prediction, here we use compute. When we are providing the training data, we remove first column. So -1 means first column is out because that is admitted or not admitted. So I'm going to run this. If you look at the head of the output, so that we just look at the first 6. So these are first 6 predictions in the training data. If you look at head training, so as an example, applicant number 2 was actually admitted, but the model predicts the chance is 37%. So in a way, it says should not be admitted. So it's an incorrect prediction. But it's a very tiny model, just 1 neuron, so it can only do so much. The reason I used a simple one so that I can also show you what kind of calculation it is doing. If you label these nodes, like let's say this is node 1, 2, 3, 4. So what is going to be input to node number 4? So that I have described here. You have this 0.0455, something like your intercept term that you see in regression. This number plus you have these weights 0.82, so something like the coefficients B1, B2, and so on. So 0.82, so this number times the actual value for GRE, which is this. This is same number, just like rounding difference is there, but same number. And then you look at 1.35 times the value for GPA. And similarly, you have negative 0.87 times the rank. So when you do that calculation and run and check what is inside IN4, it's about 1.18. So that goes as an input to node number 4. And what goes as output? So for that, there's a formula. It's called a sigmoid activation function. So neural networks, there are like different type of functions used. Here I have used the sigmoid, and the formula is 1 divided by 1 plus e raised to negative of whatever number you get as an input. Once we run that, you can check what is the output. It is about 0.76. So all this is already stored somewhere, but you may not see that on the plot because otherwise there will be too much information. So that becomes the output of node number 4. If you think of this node as node 5, so what will be input there? So again, we have that term similar to y-intercept in linear regression, negative 7.0 something, plus 8.5741, and the output we just now got. So that goes here, and you get input to node number 5. And again, output will be similar to what we did for 4. So you run that and check what is the output. Output is 0.3779. Now, if you go back and see what was the probability, 0.3779 for applicant 2. So how that was calculated, this is how it was calculated. So all these weights have been arrived at after a lot of iterations, a lot of back and forth between input and then output, and then making adjustments to the weights. How we calculated confusion matrix and classification error, and then misclassification error, 29% roughly. And if you do the same thing for test data, you get these numbers. This was just to illustrate with one single node. But what if I have 5? So how that neural network will look like? So you can plot that. So 1, 2, 3, 4. So 5 neurons. These are like fully connected networks. Each node is connected to every node, previous node, and every next node. So the idea of neural network, you may know, comes from scientists trying to mimic how the brain works in our head. So it has close to 100 billion, maybe 86 billion, I don't know what is the accurate number, but close to 100 billion neurons. And how they learn, how they interact. So those ideas are basically was the starting point for coming out with these neural network approaches. But these ideas are not new. It was there even like almost 100 years back. The only thing is now we have computing power that is making large networks possible. If instead of 5, let's say I want 5 and 2, maybe with C, something like this. Algorithm did not converge, so I may have to run it again. And once it is done, then I try to plot hidden layers 5 and 2, which means first hidden layer has 5 nodes or neurons, and second one has 2. So that's how a neural network works. The only thing is the neural network that we are talking about for large language models obviously are not tiny, but they are very, very large. Yes, Mel.
Afternoon, Professor. I just ran that and I got an error which says weights were not calculated and algorithm did not converge in one-of-one repetitions within the step math.
Yeah, so I also had the same error, right? So if you look at first time when I ran,
Oh, okay. Yep.
I had the same error. Algorithm did not converge.
Okay. Yeah.
That's why I ran again and then it converged. So yeah, because every time you come out with a different outcome if you're not starting with the same seed.
Oh, okay. Gotcha.
But that's possible, yeah.
Okay.
So this is an example that I have used myself. There's a network called a pre-trained network or model. And the name of this neural network is transfer learning. And it has been named as ResNet 50 network. When we say network, it means neural network. And 50 here is 50 layers. So the picture that I showed you had only 2 layers, like started with 1 and then 2. But this network has 50 layers. And it has pre-trained weights. So all the neurons already has been trained and a weight has been assigned. And it was trained on ImageNet data with millions of images. These models need a huge amount of data. And it had more than 25 million parameters. They had ability to classify images into 1,000 different categories. So this ResNet 50 is available, like anybody can use it. You can use it in R, you can use it in Python. I ran this in R. What I did was I gave this picture and using a pre-trained, I did not have to create myself because training this kind of model takes a lot of time and also like you need to have very powerful computing system. But I used a model which is already available and then gave a picture. So the highest score is for Norwich Terrier. And I know actually this dog is Norwich Terrier, but it also is similar to Norfolk Terrier. Very difficult to actually distinguish, but the model is able to distinguish actually. Still there is a 12% chance. And then Australian, it drops to 4 and then 4 and then like other predictions become very, very small. One of the popular LLM model is GPT-4. GPT stands for Generative Pre-trained Transformer. So this is also a pre-trained model. All the weights are already finalized. And it is a multimodal LLM. That means that it can work with text, it can work with images, and this is created by OpenAI. although like OpenAI has not released more details, but it is estimated that GPT-4 has more than 1.7 trillion parameters. So if you compare that with the human brain, which has only like 86 billion neurons, much more than that, that's how like it is able to deliver very fine-tuned output. You can think of like this picture here, like artificial brain with 1.76 trillion switches for processing language. And it's like a radio with so many knobs. So you can control different things like tonality or grammar, or whether you want the language to be soft. So many different things it allows you to customize. It is estimated to have 120 layers. And the cost was about $63 million to train this GPT-4. So when you need like so many GPUs, and that's definitely is going to be very expensive. Now, how does GPT work? We'll go through a simple example. So suppose we have this sentence which is not complete. Sun is shining and the sky is, and we want to use GPT-4. In step one, what it will do is it will break the input into pieces, and this process is called the tokenization. So GPT-4 breaks your input into small chunks called tokens. So in this case, there are 8 tokens and 33 characters. So I provided a link here. If we are using GPT-4, copy this part. I'm just going to put it here, paste it here, and this is what it says. It creates 8 tokens for these 33 characters. The sun is shining and the sky is. If you want to look at token IDs, different tokens for each word. So basically text data gets converted into some kind of number. And then in step 2, it tries to understand the context. So it looks at entire sentence structure. So it's not looking at just the last few words that used to happen in the past, but it is trying to look at the sentence as a whole before deciding what will be the next word. It captures like something like the sun is shining, so which is indicating it is a good weather, obviously. And then if you look at the part and the sky is, so the model is basically trying to come out with some kind of explanation of or description of the sky, which is consistent with the previous part, like the sun is shining. So it is trying to come out with that kind of description. So at this stage, it is already probably exploring some possible words, like it could be the sky is blue, or sky is clear, or sky is bright, something like that. And then uses the word associations from training. Obviously, like GPT-4 has been trained on billions and billions of words, and it has obviously learned that in those text, the sky is blue occurs very often. So the frequency of the time, like how often when you have the sky is, it is usually followed by blue. So it knows that. And it also knows that the words like shining, often they occur with blue sky, or sometimes like clear sky or sunny sky, something like that. So it uses like the previous data or statistical patterns or the knowledge that it has learned at the time of training. Basically, that knowledge is compressed into those weights in all those parameters, more than 1.76 billion parameters. It also tries to understand tone and intent. Like reading this sentence to GPT-4, it will sound as if like this is a positive and descriptive kind of sentence. So out of all the possibilities, GPT-4, it will rule out those that have like negative or something which is unrelated. So those things it will screen out. So sun is shining and the sky is, for example, falling. Obviously, it will rule out those kind of situations. So instead of that, it will try to focus on those words that are positive and also like they have natural kind of tone. And it also evaluates grammar fit. In the background, it is also looking at the grammar. So it sees that the sky is, so next needs some kind of adjective, and it doesn't need a noun or a verb. So it will try to rule out things like walked, for example, the sky, or anything like which is a verb or noun. It will try to rule out. Its preference usually based on the grammar will go towards something like blue or cloudy or things like that. In step 3, it is doing the prediction for the next token. So it scores thousands of possible next tokens, and it might have seen them actually in different contexts during the training of the network. Could be like blue, clear, cloudy, falling, stormy, open, friendly, like all kinds of words, and even like thousands of more. And then it assigns probabilities to each one of them. It may look at blue, for example, and based on that, it may say that it has 87% chance. Or if the next prediction is clear, it has about 7% chance. Or stormy, 2%, falling, maybe 1%, and so on. So it will use all those parameters, 1.76 trillion parameters, to figure out which word makes the most sense in this case. Now, out of these, obviously, one of them is having the highest probability because that's the most common next word it has seen during training. And it also fits very well in terms of grammar or the context. There is some amount of like probability involved, like usually, not certainly, usually it will go with the top token. But then that also depends on a term called the temperature, because usually like the way these large language models work, the idea is not to get like repetitive answers, but you ask question again, it is going to give you likely a different answer. And that is controlled by temperature. That helps to actually make this prediction less predictable in a way, and allows it to be more creative. So typically, like those people who use GPT-4, this temperature ranges from 0 to 2. The value of temperature or setting ranges from 0 to 2, where 0 means like more certain, less randomness, close to 0. Let's say if it is a 0.2. So every time, if you have set it at 0.2, every time it will give you next word as blue. But if the temperature is set closer to maybe 1, next time it may give you clear, or even first time it may say clear. Or if it is 1, it may come out with some more creative thing like the sky is in gold, something like that. Now for GPT-4, default value for temperature is 1, and that tries to balance randomness. If it is 2, obviously it could be more very random and very creative, then sometimes like it will not make any sense. And if it is close to 0, it will be more deterministic, and always you get same answers. Now, different situations, you may want it to behave differently, like if it is calculation, 2 plus 2 should always be 4. But if you are asking GPT-4 to create a poem, you don't want like same thing again and again. So it usually goes with the top token, but sometimes like it can be creative. And finally, it will add whatever token it decides on to the output and then repeat. So it will predict the next word. Like I have already added blue now. Now this process is going to repeat till finally it stops. So it again calculates probabilities for the next tokens, and it may find that today has 40% chance, with has 25%, and so on. So one cycle of completion could look like this. The sun is shining and the sky is blue with scattered clouds floating gently, something like that. So essentially what it is doing is it is trying to predict one word at a time. And while doing that, it looks at so many different things, context, tonality, grammar, and other things. GPT-4 by OpenAI obviously is very popular, and there are a lot of competitors in the market. GPT-4 is multimodal. It can generate images on your phone. You can actually talk. One of the things it doesn't have is reasoning. Gemini is by Google. This is also very hot, no reasoning yet. Llama by Meta is open source. Actually, anybody can use it freely. It's not multimodal, just text and no reasoning. DeepSeek, that came, I think, last month or so. It's not multimodal, but it can do reasoning. Cloudy by Anthropic can do both. And then you have Grok, Elon Musk XAI, not yet multimodal, but it has reasoning. And there are actually many more. And obviously, that's good news for NVIDIA because they all seem to use GPUs from NVIDIA. There's a website called olama.com. If you go to models, many of the models like DeepSeek that you saw on the previous page is available from this page. So DeepSeek's first generation of reasoning models with comparable performance to OpenAI's O1, including 6 dense models distilled from DeepSeek's R1 based on Llama and Qwen. Each one of these have multiple models available. The smallest one has 1.5 billion parameters, and the largest one by DeepSeek as of now has 671 billion parameters. So these are freely available. Anybody can download on the computer and start running them. I have provided a link here, running LLMs on local machine. Shows you like steps of how you can download and create your own large language model. Llama 4, this is Meta's model. If you click, you get more details. So looks like the input for this one could be text, multilingual text, as well as image. And it gives you all kinds of details about the model and also comparison, benchmark, comparing it with the different models. So all of these can be used actually to create your own large language model because these are all open source. Obviously, you'll not see GPT-4 here because that's proprietary and OpenAI has that. Another interesting interface is Hugging Face. So anybody can create an account. Again, this is available free of cost. And if you click on models, you can see it has all kinds of models. Multimodal computer vision, which could be image, video, natural language processing, audio, tabular reinforcement learning, and so on. Just as an example, if you look at, let's say, text classification, so many different people have generated these models and they have shared with anybody who likes to use, like Meta's Llama is also there here. This one says sentiment. So if you click on any model, it gives you details about the model. It tells you like what exactly it does. It enables a reliable binary sentiment analysis for various types of English language text. So it will tell you whether it is sentiment is positive or negative based on what you give. It also gives you all the files that were used for generating this model, and you can type. So this model is already there. You can type and it will give you instantly results. Instantly says positive 0.999, so that's like 99.9% chance this is a positive statement, and 0.001 based on the model. If I say I hate, so negative is like almost 100%. So that is one thing. You have all kinds of models, and then if you go to data sets, a Hugging Face has a lot of data actually, and you can customize like what do you want. If you want CSV, you can click on CSV. If you don't want more than 1 trillion data points, you can reduce it maybe to even 100 million is too much, maybe 100,000 and 1,000 to 100,000. So it provides you a lot of data in the CSV format. You can also classify this whether it is audio, image, text, time series, video, what kind of data is contained here. Similarly, there is something called spaces. So Spaces contains all the working models, and it can be image generation, video generation, text generation. So you can choose whatever you like. Something like this. This is a very interesting interface, Hugging Face, that anybody interested in deep learning or large language models or even multimodal models will find it very useful. This book I wrote actually late 2019 or maybe early 2020, Advanced Deep Learning with R. So all the large language models are typically, they work with text and some are multimodal. But some of the core ideas I have covered this in this book with the help of R code, so that you may find interesting. That was a quick introduction to large language models, just getting you introduced to basics and also like seeing what people are doing and where they are sharing all this information about even work in progress. So I hope you found this useful.